Hello and welcome to this video lesson on transition metal catalysts, spec reference 3.2.5.6. Our lesson objectives for this video lesson are, firstly, we want to know why transition metals make good catalysts, and also how they do that, how they operate when they're acting as catalysts. But while we're at it, let's just remind ourselves what a catalyst is. It speeds up reactions not being used up, and when it speeds up reactions, it does it by providing an alternative reaction pathway. And that alternative reaction pathway might have a lower activation energy. Than the reaction pathway that goes directly from the reactants to the product. Okay, so that's a little reminder what a catalyst does, and in the first learning objective we're going to find out how they do that, how transition metals do that when they're acting as catalysts. And then we're going to look at heterogeneous catalysts, and a couple of examples of heterogeneous catalysis. And after that we'll do homogeneous catalysis, and we'll learn all about that. So there are three things we want to cover off in this video lesson. Let's start off with how and why transition metals make good catalysts. Well, the short answer is that transition metals by definition have incomplete 3D orbitals. So elements from all the other blocks of the periodic table have complete 3D orbitals, whereas transition metals have incomplete 3D orbitals. And what that means is that electrons can be promoted to a nearby orbital, and the energy required to do that is very small. And so that is what facilitates the alternative reaction pathway, because it takes very little energy to move from one oxidation state to another oxidation state, and in that process of moving oxidation state they can transfer electrons to the reactant species, and that's what facilitates the faster reaction. So let's have a look at this alternative reaction pathway. Let's consider the reaction between reactant 1 and reactant 2, and they're going to make a product P. And we could let that reaction go ahead just by waiting for reactant 1, reactant 2 to collide and make product P. But the activation energy might be quite high, in which case we'd be waiting quite a long time for our product. So we might use a catalyst, let's call it C, in order to speed up that reaction. And so the reaction then would, instead of going off in perhaps a single step, it would proceed in two steps, such as this. And the two steps would take less time than the one step. So step number 1 might be the first reactant reacts with the catalyst and makes the product, but in the process the catalyst gets changed. It might be oxidized, for example, or indeed reduced. So let's put C to C dash is let's assume that's oxidation for now. It could be reduced, but it could be either one. Okay, so hang on a minute, you say hang on a minute, the catalysts don't get changed in these reactions, otherwise they wouldn't be catalysts. Well, just wait for a second, because step 2 might resolve our little question there, because what happens is the modified catalyst reacts with the other reactant and reforms the original catalyst, in which case the catalyst gets reduced back to its original form. And so this, let's give this an example. If we were using iron, for example, you could, for example, start off with iron 2 plus and oxidize that to iron 3 plus. That would be an oxidation reaction, and in the reformation step, your iron 3 plus would change back, would be reduced back into iron 2 plus. That's an example of what could happen. But let's look at a real example. Let's look at the contact process. Very important industrial process used in the manufacture of sulfuric acid. Okay, and in the manufacture of sulfuric acid, in the contact process, what we're trying to do in this step is that we're going to try and make some sulfur trioxide. What we want to do is we want to start off with some sulfur dioxide. We want to react it with some oxygen gas and make our sulfur trioxide, because from sulfur trioxide it's easier to get to sulfuric acid. And the catalyst we use there is vanadium oxide. It's actually V2O5. That's the catalyst. And the first step would be the sulfur dioxide reacting with the catalyst and making some sulfur trioxide. All right, but the vanadium oxide is changed into V2O4. So switching to red, let's look at the oxidation numbers of our vanadium. Here our oxidation number is 5 plus, and here our oxidation number of vanadium is 4 plus. So our vanadium has been reduced, so our catalyst has been reduced, but our sulfur dioxide has been oxidized into sulfur trioxide. So that was step 1. Step 2 is our catalyst, or a modified catalyst rather, our V2O4 is going to react with some oxygen, which is our other reactant, and be reformed back into V2O5, our original form of our catalyst. So we can see in that case, let's go through the oxidation numbers, see what's been oxidized and what's been reduced. Here we have 4 plus, and here we have back at 5 plus. So our catalyst has been oxidized by the oxygen back to its original state. And so what we can see from this two-step process is that because vanadium, our transition metal, can exist in variable oxidation states, it can catalyze this reaction. And if it couldn't exist in variable oxidation states, it couldn't facilitate that two-step process. And this activation energy, this activation energy for step 1 is very low, and the activation energy for step 2 is also very low, whereas the uncatalyzed reaction has a very high activation energy. So that's why they proceed much faster as a catalyzed reaction. So there's two types of catalysis. There's heterogeneous and homogeneous catalysis. Heterogeneous catalysis, let's define that, and that is when the catalyst is in a different phase from the reactants. And usually the catalyst is the solid and the reactants are gases. And you need to be familiar with three examples of heterogeneous catalysis. And the first one we've done already. The first one is the contact process. And you'll remember that that uses vanadium oxide, vanadium 5 oxide, to make sulfur trioxide out of sulfur dioxide. And the second one is the Haber process, which you'll remember is the way that we make ammonia, which is used to make fertilizers. And that starts off with nitrogen and hydrogen and makes our ammonia. And of course all of these are in the gaseous phase, whereas our catalyst, which is an ion catalyst, is in the solid phase. And so the fact that we have a solid ion catalyst with gaseous reactants makes that heterogeneous catalysis. So that's number 2 example, and number 3 example is with catalytic converters. That you find in exhausts of cars. And they perform a very useful function. They take what would otherwise be poisonous gases from going into the air. We've got carbon monoxide would be created from the incomplete combustion of our petrol or diesel. And also we would get some nitrogen monoxide, also a nasty gas. And what happens is that our catalyst, which in this case is rhodium, also a solid, converts the carbon monoxide to carbon dioxide, right? And it converts the nitrogen. In the process, it converts the nitrogen monoxide to nitrogen gas. Very useful. Nitrogen gas, not harmful at all. Carbon monoxide, not harmful to us, even if a little bit harmful, quite harmful to the environment. So there we have 2 examples of heterogeneous catalysis. But before we move on, what we must do is cover 2 more little concepts here. The first one being about support media, I suppose, for heterogeneous catalysis. Here in the diagram we have the underside of a car, and you can see the start of the exhaust pipe. This is the exhaust pipe here, and at the start of the exhaust pipe is this unit here, which is the catalytic converter. And you can see even from the outside it's sort of a lattice shape. It's made into a lattice shape, and that lattice shape is like a honeycomb sort of shape. And what that does is it provides a high surface area. And so the reaction of carbon monoxide and nitrogen monoxide, the reaction is not only sped up by the fact that you're using a catalyst, but also that there's a very high surface area on which the reaction can happen. And that's provided by the honeycomb shape or the lattice shape of the catalytic converter. And so that's feature number 1 of catalytic converters. Feature number 2 of catalytic converters is that they are coated with the catalyst, as opposed to being made from solid catalyst. So the reactions, this reaction here of carbon monoxide and nitrogen monoxide to carbon dioxide and nitrogen, that reaction happens on the surface of the catalytic converter. And so it doesn't really matter what the middle of that catalytic converter is made of. It only matters that the surface is made of rhodium. And so you just coat it, you just coat some ceramic. So the middle of it is made out of ceramic, which is easy to shape in a lattice shape and also cheap, much cheaper than rhodium. Right, so that is the second feature of catalytic converters that you should be familiar with. One is that we just coat a cheap material with our expensive catalyst. And the second is that we shape them such that we provide a very high surface area on which the reaction can happen. Good, and so that little subtopic there is called support medium. Let's say support medium required for heterogeneous catalysis, because of course you've got your catalyst as a solid and your reactants as gases. Okay, so that's the one subtopic on heterogeneous catalysis you need to be familiar with. The other one is about poisoning catalysts. Let's use this space here. Poisoning catalysts. And poisoning catalysts are bad because if a catalyst is poisoned, then it doesn't speed up the reaction as much as it does speed up the reaction if it's pure. So the reaction is slower. And it's also bad because you have to replace your catalyst. And both of those reasons mean that money is wasted. And we don't want companies to waste money, because then our goods are more expensive for us to buy. So that's the problem with poisoning of catalysts. Let's have a look at how, for example, our iron in the Haber process might be poisoned. And so the poison is sulfur. In fact, the sulfur, if there was sulfur present in this reaction, would bind to the iron and stop our nitrogen and hydrogen contacting the iron catalyst. So the sulfur is bad, and so we'll draw a cross through it there. That's the poison. But where does that sulfur come from? It comes from the hydrogen, as it happens, because where do we get the hydrogen from? The hydrogen is made from methane, and the methane is made from natural gas. And the natural gas might contain sulfur impurities in it. So in that process of manufacturing your hydrogen, you must remove this sulfur from your natural gas before it is turned into hydrogen. Otherwise, our Haber process wouldn't be as efficient as it is. We wouldn't get the fertilizers that we need, and our food would be much more expensive, and there'd be less of it. So that's one example of catalytic poisoning. The other example is here with lead. So lead, Pb is lead. And this is a bit of an old-fashioned bit of information, to be honest. But if there was lead present in our catalytic converters, that would poison our rhodium. So the lead would bind on to our rhodium surface and inhibit the conversion of carbon and nitrogen monoxides to carbon dioxide and nitrogen. So we're going to draw a cross through our lead there. Where might that lead come from? Well, it doesn't exist in petrol anymore, but it used to be that you could buy leaded petrol. Lead was in the old days added to petrol to stop engine noise. But of course then it was discovered that not only is lead poisonous to us, so it would end up in the atmosphere, we'd breathe it in and get poisoned by the lead, but also it destroyed the catalytic converters as well. So our carbon monoxide and nitrogen monoxide would get into the atmosphere. So I'm going to just write down petrol to summarize that little spiel there. Okay, so that's heterogeneous catalysis, and we're going to move on now to homogeneous catalysis. And the first thing to say is that homogeneous catalysis, as I'm sure you can guess, is when our catalyst and our reactants are in the same phase. And usually that means that everything is aqueous solution. So our catalyst is in aqueous solution and our reactants are in aqueous solution. And if that is the case, then we're talking about homogeneous catalysis. And what I think we'll do to start with is to have a look at an old energy profile diagram to illustrate the speeding up of reactions. So what we have here is our reaction pathway. Well, let's say our reaction progress. And this is our enthalpy. And let's say, for example, we have a exothermic reaction. So we've got our reactants here and our products at a lower enthalpy. And our uncatalyzed reaction, let's draw an uncatalyzed reaction in blue. So our uncatalyzed reaction has a high activation energy. So let's illustrate that in red. So this enthalpy difference here is our activation energy, where the red one is our uncatalyzed reaction. And let's switch to purple now and do our catalyzed reaction. Now, as we've illustrated before, catalyzed reaction often happens in two steps, each of which has a lower activation energy. So it might proceed to the intermediary like that, and the intermediary then it goes in step 2 before you get your products. And this energy here would be our activation energy for our catalyzed reaction. And also this little energy here would be the activation energy for our second step, but that's usually smaller than the activation energy for the first step. So we label the larger activation energy as the activation energy of our catalyzed reaction. So let's just label these as our intermediaries. Which might be the catalyst in its adjusted format. So as you can see, the activation energy is of our alternative reaction pathway, our less than, our uncatalyzed activation energy, and therefore this reaction would proceed a lot faster because more of the reactant molecules would have sufficient energy to create a successful collision. So what we're going to do now is we're going to do an example of one such heterogeneous reaction, and that is when we react ferrous disulfate and iodide ions using an iron 2+ catalyst. So let's write the uncatalyzed reaction in red to be consistent. So we've got our peroxide disulfate ion, which has a 2- charge on it, and that of course is aqueous. So of course, because it's homogeneous catalysis that we're talking about, and we're going to react that with 2 iodide ions in solution, and they're also minus charged. And then that's going to make an iodine molecule dissolved in water. And we also get a couple of sulfate ions as well. Okay, so that's the uncatalyzed reaction, and I think you could probably see, if you notice, that both of our reactant ions are negative, that they would struggle to collide because the negative charges would repel each other. And so before they were getting to collide, they'd repel each other and wouldn't collide. And so that reaction is going to happen very slowly. So instead, what we want to do is we want to use a catalyst that avoids that problem, and that catalyst is iron 2+ ions. So if we used iron 2+ ions, what we could get is we could get our peroxide disulfate ions to react with our catalyst, which is our Fe2+ ions. And those Fe2+ ions are going to be oxidized into Fe3+ ions. So that's the other variable oxidation state of iron. So we've had the catalyst being oxidized, so it's reduced our peroxide disulfate to 2 sulfate ions. Like so. But we can't leave it like that. That's only the first step of the reaction. The second step of the reaction is when our Fe3+ ions are converted back into Fe2+ ions, so they're reduced back. So they are oxidizing our iodide ions, and making them into an iodine molecule like that. And of course everything happening in aqueous solution. Like so. And you could test for our iodine with starch, as I'm sure you've done at some stage in your chemistry career. And so what's interesting about this? Well, again, it's another example of the catalyst being a transition metal and having the useful function of being able to exist in variable oxidation states, in this case 2+ and 3+. So in the first step we've got our iron 2+ ions being oxidized into iron 3+ ions, and in the second step we've got our iron 3+ ions being reduced back to iron 2+, and in the process you have converted our iodide ions into our iodine, which was our purpose all along. And the other interesting thing about this is the fact that we had our 2 negative ions repelling each other, being the reason why the reaction wouldn't happen fast enough in an uncatalyzed way. Okay, so that's the first example of homogeneous catalysis. On the next slide, we're going to do another example of homogeneous catalysis, but it's also an example of autocatalysis. Yes, here we have it. Autocatalysis is where a product of the reaction also catalyzes the reaction. And so an example of that would be when manganate reacts with ethanedioate ions. So that's an interesting ion. It's 2 carbons, 4 oxygens, 2 minus. And they're going to make some manganese 2 plus, along with some water and some carbon dioxide. And just balancing that off, you need 10 carbon dioxides made. Because you start off with 2 of these, you need to add 16 H pluses as an acid, and you need 5 of those, 2 of those, and you make 8 of those. So what we've got here is the complete reaction, and everything's aqueous. Save me writing aqueous everywhere. So it's a homogeneous catalysis situation, but you'll notice that again we have negative charges on our reactants, and so it's going to react slowly to start with, but as the reaction proceeds, we are going to get some manganese 2 plus ions created, and when we do get some manganese 2 plus ions created, then we can have an alternative reaction pathway. So here's step 1 of the alternative reaction pathway. I'll do that in purple, I think. So step 1 of the alternative reaction pathway would be when we've got some manganese 2 plus ions, and they're going to react with some manganate ions. They need a bit of acid particles to help the process, and when they do, they're going to make manganese 3 plus, which is our modified catalyst. Again, you can see manganese, the transition metal, is acting in 2 different oxidation states, and we get some water off as well. So that's step 1, and then step 2, well, let's balance that first before we do step 1, just for completeness. The balancing really isn't important here, but hey, we're chemists. Okay, so that's balanced now, and so once we've done step 1, now and in fact what we've done is we've converted our manganate into one of the products, which is water. Then our catalyst has also been oxidized into from manganese 2 plus into manganese 3 plus. So now we have to reduce that manganese 3 plus back to manganese 2 plus. So let's start off with our manganese 3. So our second step, our manganese 3 plus, and we're going to make it back into manganese 2 plus by reacting it with the other reactant, which is our ethanedioate ions. And in that process, we're going to make our other product, which is carbon dioxide. Now we'll just balance that, so we need 2 of those, and we're going to make 2 of those and 2 of those. So the usual 2-step process whereby we've used the useful facility of transition metals being able to exist in variable oxidation states. So in the first step we had an oxidation of the catalyst, and then we've reduced it back to its original form in the second step. And in those 2 steps we have first of all created one of the products, which was the water, and in the second step we created the other of the products, which was carbon dioxide. and in the process we've also used up the first reactant in the first step and the second reactant in the second step. So there we have the catalyzed reaction, which happens when we get the catalyst created, which was not added to the reaction mixture, but was actually one of the products from the uncatalyzed starting reaction. So what we're going to do now is we're just going to do a little graph of that reaction, and we're going to draw that with a concentration against time graph. So at the start, let's say this is the start because it's at time 0. At the start we've got a high concentration of reactants. So concentration of reactants, and at the start it's high, and it doesn't change much at the start because our reaction is slow, because we've got our two reactants as both as negative ions, but some of them do end up colliding, and when they do so they make the manganese 2+ catalyst ions. So as we do get some of the manganese 2+ ions created, they act as a catalyst and therefore will speed up the reaction. So the concentration of the reactants decreases very quickly until they're basically all been used up, in which case the reaction slows because there's not many reactants left, and eventually it's 0. So we've got 3 phases, 1, 2 and 3, and very quickly phase number 1 is the slow start because it's uncatalyzed. And we've got the fast middle because a catalyst has been produced in the early reactions. Let's call it auto-catalyzed. And then the third stage is it slows at the end because the reactants are used up. And so that is an example of autocatalysis and also an example of homogeneous catalysis. And we might do that practical in class as it happens. So that brings us to the end of this video lesson. Let's just, as we usually do, let's just make sure that we've covered everything off we intended to. Why do transition metals make good catalysts? Well, that was about their incomplete 3D orbitals, allowing them to be of variable oxidation states. And heterogeneous catalysis was all about solid catalysts with gaseous reactants, and we looked at an extra couple of examples of that, and we also noted how catalytic converters, noted a couple of features of them, like the surface area, and we also looked at poisoning as well. So we've done heterogeneous catalysis and homogeneous catalysis, where we've got everything in aqueous state. And we looked at not only a normal example of homogeneous catalysis, and we drew a little energy profile diagram to show how the 2 steps with their lower activation energies could speed up the reaction. We also looked at another homogeneous catalysis example, which was also an autocatalysis situation. So I think we've done all 3 of those lesson objectives, and hopefully that's been clear for you.